So we said in the previous video that we could use differentials to estimate the error in a calculation due to errors in measurement. So this picture here, what it's basically doing is it's saying, okay, we'll probably write on top of this at this stage. So this here is a measurement. That's right, measurement. This is the true value, which is made up of the measurement plus an error. This is your calculation. And you make your measurement. Say, for example, this could be the area of a square, for argument's sake. You measure the side length, you bang the side length into a formula, you get your calculation. But you should be a little bit more careful, because any measurement comes with an error. So the true is composed of the measurement plus the error, and then this would be the true value, say for argument's sake the true area, and this is the error in the calculation that is due to the error in the measurement. And what we're going to do is we're going to estimate this error in calculation using differentials, where you do the derivative of the thing you're calculating with respect to the times the error. So kind of putting it in this framework, we have, so you got some variable p which depends on a and b. So a is a variable, b is a variable. You measure both of them, you get, say, a0 and b0. That's fine, but then there's associated errors. So the errors can be due to all kind of different things. For example, if I use this, the error is going to be 1 millimeter. It's a precision error. Or maybe a voltmeter, it's like the error is 10% of what you got. So if you measure it to be 3.2 volts, the error will be 0.32 volts. All these kind of things. Or sometimes you have to estimate the error. So what we're going to do is, we have measured A and B, A0 and B0. We bang them into the formula. We get a calculation of P. Now the question is, well, what about the errors in the measurement of A and B? How will they convey uncertainty? How will they give uncertainty into this calculation? Basically how we do this, and I'll just kind of write down this formula, is we say, okay, the error in the calculation of P is going to be estimated by a differential. Now, because it's a function here of two variables, and we can do three variables as well, we're adding them together. There's all kind of manner of possibilities. If you measure something, say for example the area of a rectangle, there's every chance that you overestimate the width, underestimate the length, and actually that causes the two errors to kind of cancel each other out. But you can't be guaranteed that that happens. So what you want to do is take a worst case scenario. Okay, so what we're going to say is, rather than this change, okay, we're going to take the absolute value, so it'll be dp, and we're going to take the max. Now how we do the max is we just make it the worst case possible. The error actually could be anything from minus the maximum error to plus the maximum error. What we're going to do is we're going to say, okay, just make it all bad. Make it as big as possible. Make everything positive. So what we'll do is we'll take the errors to be positive, and then we'll take the absolute value of this. Now actually what that's doing is, really you're choosing, you just make this positive. So choose this to be positive, and by taking the absolute value, make this positive. Now really what you're doing is, what that is the same as, if this thing turns out to be negative, take the error to be negative as well. And if minus by minus is plus. Now it's kind of hard to write that down, so instead what we do is take the error to be positive and take the absolute value. And that'll give you the worst case scenario. So partial derivative of P with respect to A times error in A, plus derivative of P with respect to B times the error in B. And these are, they don't look it, but they're differentials because it's derivative times error. Derivative times error, derivative times error. This is actually a change in the calculation. This is a change in the calculation. This is due to errors in measuring A. This is due to errors in measuring B. Add them two together, you get an approximation of the error in the calculation due to both of the errors, measurement errors. Okay, this is what we're going to be using. So here it's kind of explained on top. The reason that we use absolute values is because we don't want errors to cancel each other out. You don't want to predict that because the errors could be negative and they could kind of all conspire to give you a bad situation. The partial derivatives are evaluated, the measurements in this formula is not in the tables. Typically we'll have a quantity that depends on two variables, possibly more. You'll be given measurements, you'll be given errors, and your job is to present the calculation. I think this is what it is, plus or minus the error. And here is something that we should do. The approximation of the error in the calculation by the differential is rough, and because of that you should round this to one significant figure. You can't be more precise than that. And if you think about it then, if the error, say, is 0.3, there's no point talking about stuff after the first decimal place because it's within the margin of error. So you should match the number of decimals in your calculation with your error. And of course, as engineers, we should use units. So we've got 3 examples and we will look at them in the next lecture video.